Refining petroleum, okay. So many organic chemicals are synthetically prepared using petrochemicals. So a basic hydrocarbon such as ethene or propene are things that can be converted into plastics. So plastic water bottles. In university we made plastic garbage bags basically, or plastic grocery bags you can make from these things. This mixture must be separated, of course. It's made by refining petroleum. And it has to be separated into different types of structures here. So the individual components are recovered as pure hydrocarbons. About 95% of all petroleum that's refined, so anything that we refine from these hydrocarbons, usually is burned as some type of fuel. So things like gasoline, jet fuel, kerosene, propane, things like that. Okay. The remainder can be used for fertilizers, pharmaceuticals, plastics, things like that. So you could actually get some of those things from that. All right. So fractional distillation is probably the main thing that you need to know about what we're going to talk about today here. Fractional distillation is the first step in the refining of petroleum. The different boiling points of hydrocarbons, so it's based on boiling points, allows them to be separated into different, what we call fractions, or different sizes of molecules. Okay. The boiling point of a hydrocarbon increases as the molecular size increases. Remember, hydrogen bonding, yes, plays a role in things like that, but as far as the size of a molecule, remember, the really short ones tend to boil and melt very quickly, low temperatures, right? And as you get longer and longer, you're getting more and more carbons. The more and more carbons you get, the more electrons you get, and the longer that chain becomes, right, the more electrons you have spinning around and around. That's London forces, right? So the longer they get, they have higher melting boiling points. Long carbon chains have high melting boiling points. The middle ones are a little bit lower, and the really small ones are lower yet. Okay, so we're going to use that to our advantage, and we're going to basically boil these at different temperatures here and collect them, okay, into different fractions. When petroleum is heated to a very high temperature, it vaporizes into gases. So actually the first step in a fractional distillation is to boil the gas. Okay, so you vaporize it, you turn it into a gas. The less dense gas rises up the tower. As it moves towards and away from the heat source, it begins to cool down. And I have a diagram here, and we'll go over this with the diagram as well. Different hydrocarbons, if the heat source is down here, as you get farther and farther away from the heat source, the gas begins to cool. And what happens is, as you get higher and higher, eventually the gas will cool enough to condense back to a liquid. And when it condenses into a liquid, that's where you can collect it. Okay, and I'll give you some examples of that coming up here. Okay. The largest hydrocarbons will condense at the highest temperatures, so they will condense usually very close to the heat source. The smallest hydrocarbons will probably condense at the very top of the fractional distillating tower, and because they have the lowest melting boiling points. And if you think about boiling point, what is that? It turns from a liquid to a gas. Well, we're doing the opposite. We're doing condensation. So you can think of it as, it is a gas. When is it going to cool down and turn into a liquid, basically? That's going to be farther away from the heat source. Okay. At each level, pipes channel liquid fraction away for further treatment, and fractional distillation towers can be quite tall. They can be 60 meters tall. Okay. All right, next. You guys have this diagram. This is what a fractional distillating tower looks like. All right. This is just one. Obviously, this isn't perfect or anything like that, but this is just one diagram, or the one that we'll use anyway. What you'll notice, they all kind of look the same. So what do you have to know about this? You have to kind of understand how it works, and you have to know that this is fractional distillation. Those are probably the two things. So your crude oil comes in here. Okay, basically oil that is refined, maybe from the oil sands or something like that. The crude oil will come in here. They have a steam thing here, and that steam is set at a specific temperature, and this one here, I'd say that steam is probably somewhere around 426 degrees Celsius, okay, roughly. What happens is the crude oil comes into here, okay, it's a liquid right now, and it vaporizes into a gas right here, okay. Now, this is at 426 degrees Celsius, so if the boiling point of that crude oil, that boiling point of that hydrocarbon is higher than 426, it's not going to turn to a gas, the boiling point. Let's say the hydrocarbon has a boiling point of 500 degrees Celsius. Is 426 degrees Celsius, I can't write on here, otherwise I would. Is 426 degrees Celsius enough to turn a hydrocarbon that boils at 500 to a gas? No. So it's going to fall down to the bottom here, and it's going to be a liquid, all right? And it's going to be collected here, and things that we use that for are some examples are asphalt, lubricating oils, waxes, and usually those have more than 20 carbon atom molecules, okay? So something like C25, for example, something along that line there, okay? Now, this crude oil that comes in here has many parts to it. So there's going to be some hydrocarbons that, yes, have a boiling point of 500, and there's going to be some hydrocarbons in that crude oil that boil at, let's say, 250, we'll say. Okay, so here we go. 250 degrees, let's say this particular hydrocarbon boils at 250. So 426, has it turned to a gas? Sure, that's enough temperature to turn it to a gas if it boils at 250, yes? So it's going to start rising up this way here. So it's going to start going up through these, basically these columns here, okay? And what's going to happen is it's going to keep going up, and we're going to get far enough away from this heat source here. As the gas travels up, it starts to cool, right? Because we're getting farther and farther away from the heat source. So it's going to start to lose energy. Gets to here, 250 degrees Celsius. That's far enough away from this heat source to cool it down to 232 to 426 basically. So 250, is that going to condense back to a liquid now? Sure it is. So at anywhere, basically they're saying the boiling point from 232 to 426 here, that part's going to get fractioned out here. So at 250, okay, it's going to be cool enough to get collected out here. All right, and at that point you would use that, for example, for things like gas oil, diesel fuel oil, things like that. Generally speaking, it's 18 to 20 carbon chains. You don't need to know that part, but that's what would happen there, okay? You know, if you don't understand that, hey, let's use something we can think about. Now I realize water is not a hydrocarbon, but it would kind of go on the same principle, right? It would come in here. It's 426 degrees Celsius. Is water a gas? Yep. It would start going up here. 100 degrees Celsius. Well, 232 is the lowest number here. It'd still be a gas, yeah? So it keeps going up. 157, still a gas. Keeps going up. 104, still a gas. Keeps going up all the way up to here, where it finally cools down enough to condense as a liquid and would come out here. Yes? Once again, obviously, water is not a hydrocarbon, but that's something you guys can probably relate to a little bit easier. Okay? You know, and then this part here is naphtha, refined oils, 12 to 15 carbons, and then this is the straight run gasoline stuff, 5 to 12 carbon atoms. Now, after that happens, after it goes through this fractional distillating tower here, and like I said, basically at the top here, gases up to 32 degrees Celsius, usually 1 to 4 carbon atoms up there. So things like propane would come out the top, basically. Things like that, because they'd still be a gas. Okay? Methane, things like that. Okay? So that's how that works, and basically you have to understand that it's going to come in here, okay, and basically it's going to, it's turning to a gas, it's being vaporized, and the gas travels up until it basically condenses, and in some case it never does condense, it just leaves the top as a gas, okay. Now that's fine, but you can see obviously, you know, 12 to 15, 5 to 12, 5 to 15, 18, even the top one, 1 to 4, that gives us quite a range of different types of hydrocarbons that are coming out of that different columns there. So the next part is more refinement, basically. All right? And how they do that is through, well, a couple ways. Cracking and reforming are two terms that you probably need to know. Okay? They are techniques that can convert a hydrocarbon from a less useful one to a more useful one, basically. Okay? Some of the stuff that we get out of here is not really that useful to us. Okay? So we need to further refine them to get them to something, you know, that we use more of, like gasoline, for example. It just doesn't come out as gasoline. We have to refine it further to get useful gasoline for our car engines and things like that. So naturally occurring gasoline fraction is not nearly enough to meet the market demands. It gives you too large of a supply of heavier hydrocarbons, basically fractions, so we need to refine it further. Okay? Two ways to refine things are cracking and reforming. You'll see here, this is the same tower we just had, but now you can see the extra add-on parts that further refine it. Okay? So we go through things like catalytic reforming, which we'll talk about in a second. Hydrocracking, which is the addition of hydrogens into there. So, you know, we're actually going to do this one as one of our reactions, so we will focus on this. When you have an alkene or an alkyne, you have double and triple bonds, yes? If you add in hydrogens to those, if you had a double bond and you add in hydrogens, you can make that alkene into, this is like gangster stuff. You can make the double bond. If you add in hydrogens, you can make it an alkane, okay? And if you add an alkene, west side, okay, you can make it into an alkene, alkyne to alkene by adding in hydrogens. All right, so that's something called hydrocracking, or we're going to call it addition, okay? There's catalytic cracking and things like that. So there's different forms here that we can do. Look at all the stuff you can get from this stuff here. Cooking, plastics, fibers, drugs, detergents, synthetic rubber, airplanes, automobiles, farming. You don't get airplanes from that, but you get fuel for it. Okay. Home heating, jet fuel, you know, rail engines kind of thing, diesel fuel for rail engines, factories for ships, roads, lubricating oils, wax paper, things like that. Okay. So it says Coke, not Coca-Cola, different. Okay, we'll talk about it in a second here. Listen, so a couple things you should know. Okay, you need to know the tower, how it works basically, but you also need to know probably a little bit about cracking. Cracking in general, think about like an egg. You know, what do you crack in the morning? You crack an egg. You crack an egg, you get one thing, turns into two parts, right? Crack it, you get the shell breaks apart, yeah, two parts, usually sometimes five, right? And then sometimes the shells are in the egg, and then you got to pick them up. Anyway, cracking. So you're making something, you're taking something larger and making something smaller from it, and usually you get a couple things from it. So for example, you don't need to know the equation or anything like that. Well, I'll tell you the equations you're going to do here. None of these. Hexane under steam and pressure gives you propane and propene. Okay. So when you apply steam and pressure, it cracks carbon to carbon bonds, and you can get two smaller things from it, okay? And that might be useful in the use of gasoline and things like that, okay? So cracking converts larger hydrocarbons into smaller ones. You should know that. You should know that thermal cracking involves high pressure and temperature to basically make that happen, okay? To make the large one turn into two smaller ones. That's all you need to know about that, okay? Once again, you'll have to, you know, it's not enough just to crack it. So break it apart, for example, you usually have to refine it further again. So after you crack it, you will have to refine still. Catalytic cracking is a low pressure process, and it passes a powdered catalyst through a heavy hydrocarbon fractions at fairly high temperature, 600 degrees Celsius. So catalytic, of course, uses a catalyst to speed that up, okay? Hydrocracking involves the addition of hydrogen gas during the catalytic cracking process, which turns alkenes and alkynes into more stable alkanes. All right. So, generally speaking, cracking is taking a bigger one, making two smaller ones out of it. Maybe more in some cases. Reforming is exactly like it sounds. Reforming takes a hydrocarbon and reforms it into a different type of structure that you may find more beneficial or that we need more of. So for example, I think one of the examples they give you here is heptane. Okay? Heptane doesn't burn particularly well, but when you reform it, methylbenzene into methylbenzene, which is a reforming process, so you're taking that 7-carbon chain and you're reforming it into a circular kind of structure or cyclic kind of structure, that tends to burn very well in car engines. Okay, so reforming takes a 7-carbon chain and reforms it into a 6-carbon ring with an add-on kind of thing, perhaps. Once again, you don't have to know the equation for that to happen, but you just have to know that reforming rearranges them into a different structure. Okay, and that's basically reforming there. And the other one that you will do here, or that you will know kind of thing, we have our kind of own version of this, but alkylation is a reforming process in which smaller hydrocarbons are chemically joined together to make a larger one. So cracking takes a large one, makes 2 smaller ones. Alkylation takes 2 smaller ones and makes a larger one, kind of the opposite. Okay. And once again, we have our own. We're not going to focus on these 3 types here. We have our own reactions that we're going to focus on. They're a little bit simpler than some of these here. We do addition, elimination, substitution, and esterification are the ones that we focus on, are the 4. Okay. That Coke that you're all interested in making, Coca-Cola or something, that Coke is basically the residue that falls out the bottom. If you remember in the fractional distillation tower, it's the very, very heavy stuff. Okay. That stuff is good for burning, so we usually use it for power generation, is the bottom stuff that falls out of that fractional distillation tower. Those are the really, really large hydrocarbons. Okay, so that's probably the stuff that you need to know from this, like I said. Anything else there is probably a little bit of extra stuff that's, it's probably a little bit just extra information for you. So if you want, obviously take a read through that, and you should read through it, of course, but that's kind of the main stuff that you'll need to know. All right.